Hello students, and welcome to a new lecture about electronegativity and polarity. We will be looking at the polarity of the bonds and how does that affect the polarity of molecules. Now remember, we talked about the definition of electronegativity as the ability of the atom to attract electrons within the covalent bond. Polar covalent bonds are bonds in which the bonding electrons spend more time closer to one atom than the other, and that atom normally is the more electronegative atom. The larger the electronegativity difference, the more polar that bond. We have looked at this before. If we have two oxygen atoms bonded together, then the electronegativity difference will be 0, and that will be a non-polar covalent bond. If there is slightly difference between their electronegativity, that will create a dipole in which the electrons are going to be heading towards the more electronegative atom, in this case nitrogen, and that will give me a polar covalent bond. If that difference even get bigger and bigger, of course there will still be a dipole heading towards the more electronegative atom, in this case oxygen, and that will give me a polar covalent bond, except that this one will be more polar than the previous one. If the electronegativity difference is really large, then there is no more sharing electrons. There is losing and gaining, because in this case if fluorine is way more electronegative than lithium, it will totally steal that electron, gains it, and become an anion and a cation. No partial charges, full charges in this case, and that makes ionic bond. So in this specific case, let's label each atom with either a partial negative or a partial positive. What atom is more electronegative, fluorine or sulfur? That should be an easy question, knowing that the fluorine is the most electronegative atom. So anytime I have a bond with a fluorine, the dipole is going to be heading towards the fluorine being the more electronegative, which will place a negative partial on fluorine and a positive partial on sulfur. Phosphorus and oxygen. In this case, oxygen is the more electronegative atom. Therefore, I'm going to have the dipole heading towards oxygen, partial negative on oxygen and partial positive on phosphorus. This here is a molecule which is hydrogen fluoride. However, this molecule is made of only one bond. So the polarity of the molecule will follow the polarity of that bond. There is higher intensity of electrons on fluorine, the more electronegative atom, which leaves a poor electron density on the other end, which is hydrogen in this case. So that's the electron poor region, and the red one is the electron rich region. And the dipole is heading towards the fluorine, which is the partially negative atom, and the molecule polarity is following the bond polarity, because the whole molecule is made of one bond. The dipole moment, which is mu, can be calculated by multiplying the charge with the distance between charges, and the units for that is dBi. Hydrogen fluoride has a dipole that's negatively going to, partially negative charge going to be on fluorine and partially positive charge on hydrogen. Now, what about molecules that are made of more than one bond? Polar molecules, what makes a molecule polar? It means that one region of that molecule is having more intensity of electrons than the other region. There is uneven, distribution of electrons. As we said, if the molecule is made of one bond, then the polarity of the molecule will follow that specific bond. In hydrogen chloride, another example in which the molecule is made of only one bond, then the polarity is following chlorine, which is more electronegative than hydrogen. Now, a nonpolar molecule can contain polar bonds if they cancel out. Meaning, what we're trying to get out of this, if all the bonds in the molecule, please pay attention to this fact, if all the bonds in the molecule are nonpolar, then the molecule is also nonpolar. It is when the bonds are polar that you can have two scenarios. If the bonds are polar and they are not evenly distributed and pulling electrons to one side, then that molecule is polar. But if the bonds are polar and they are canceling out, that will lead to a nonpolar molecule. So here is an example of a molecule with polar bond. This is carbon dioxide. The oxygen-carbon bond are polar. However, they are equivalently in magnitude and opposite in direction. So this is like pulling the rope. If one team is pulling exactly as the other team, then the rope is not moving. Now think of electrons. They are trying to be pulled to the right, but with the same strength are pulled to the left, they're not moving. So that makes carbon dioxide to be nonpolar because these two dipoles cancel out. Now in ammonia, which is this next molecule here, you're having lone pair and you're having hydrogens. And now there is the lone pair, which is electron density, and every lone pair I normally place in a bunny ear and make the direction of that as a dipole because this is where electrons are heading in the lone pair region. And there is also these dipoles going towards nitrogen in these polar bonds. Now look at how everything is heading up to the nitrogen, right? Which means that north side of the molecule is high density of electrons, which will leave the hydrogen end of it to be very poor in electron. So that makes a polar molecule. Same thing here for water. In water, if I'm going to draw it to you in a way, so you have two bonds and two lone pairs. Put them in a bunny ears again. This one is heading up, this one is heading up. If I call this dipole 1 and this is dipole 2, and if I add 1 to 2, it will give me dipole A. This is, by the way, a topic in math called vectors, so you may want to go over that topic to remind yourself of how to do it, okay? If I add 1 to 2, it's going to give me dipole A, which is heading in this direction. This is A. Okay? Now, the next dipole, let me actually change color just to make it clear. So this here, A, is the outcome of adding 1 and 2. Now the next dipoles that I have is dipole 3 and dipole 4. So this is here is dipole 3 and this is here is dipole 4. So 3 and 4. And if I add 3 to 4, that should give me dipole B, which will be this dipole here. So the total net dipole of the molecule is to add A plus B. And if I add B plus A, and both of them are heading north, that's going to give me this outcome. So the net dipole of water is this. It's a huge dipole heading towards the oxygen atom. So no doubt, not only that water is polar, water is very, very polar. Now, another example here is to show you nonpolar molecules. We did talk about this example like carbon dioxide. They are going in opposite direction. Another one will be, for example, boron trifluoride. Now, although this here is having strong dipoles heading towards all the fluorines, dipole 1, 2, 3 will cancel out. The reason for that, if I add 1 to 2, that's going to give me A, and this is how A look like. Now, if I add A to 3, that's going to give me 0 because A plus 3, similar magnitude. Why is it similar magnitude? Because it's the same bond. Boron, fluorine, single bond, yet opposite direction. So 0 net dipole, therefore the molecule is non-polar. Now, if you have two dipoles going in that direction, Then if you add them up together, they are not canceling out. That will make the molecule to be polar. If you have a tetrahedral, like this molecule right here, then if you add this dipole to this dipole, so this is dipole 1, dipole 2. If I add 1 to 2, it's going to give me A, and A is heading in this direction. And if I add dipole 3 to dipole 4, 3 plus 4 is going to give me B, and this is how B will look like. Now look at A plus B in this case looks like this. I'm adding this one to this one. Equal in magnitude, opposite in direction, 0 net dipole. This molecule is non-polar. Again, because all the atoms are the same, so the same bonds. This here was the model that we have shown for trigonal pyramidal like ammonia. There is no, all dipoles are going in one direction. For example, here, if I put like a fluorines here, for example, or you know what, let me take this and just keep the directions for you, so to simplify the pictures, right? If all your dipoles are heading in this direction, then that directions here, like if you go this way, and this way, and this way, you can see all of them are heading towards, you know, the lower end or south. So therefore, there is nothing canceling them out. So that will give you a polar molecule. So to put it in a practical term, how do you even know that? You first draw the Lewis structure. Then you put Vesper, because who's going to tell you about the directions of the dipole? You need to know the direction from the geometry, the shape. And the only way for you to know the shape is if you know Vesper. Now look at these molecules here, right? This is a molecule made of one bond. That bond is polar. The molecule is therefore polar. These are dipoles heading in one direction. No other direction is canceling them. So that's polar. This is a tetrahedral, equivalent atoms and bonds all over. That makes the molecule to be non-polar. Now look at this molecule. Why is that polar? Because please make the following note. These bonds, and make this for you, any carbon-hydrogen bond is always going to be considered non-polar due to almost very small, very small electronegativity difference. So anytime you see a molecule that's only made of carbon and hydrogen, so if I give you this molecule and I tell you, I am asking you to predict its polarity, you immediately have to conclude it's non-polar. Why? Because a molecule like that is either made of carbon-carbon bond, which is naturally non-polar, same atom, or a carbon-hydrogen bond, which are also non-polar bonds. So this molecule here, I don't have any polarity. I only have one polar bond going in this direction. Nothing is canceling this dipole, so that makes this molecule to be polar. Now I want to also show you another example here. What if I have a molecule like this one? All these bonds are polar, right? But the dipole will not be the same, meaning the dipole for a fluorine bond will be larger because fluorine is more electronegative than chlorine. So now here you go, you cut the balance. If this is 1 and this is 2, and you're going to add 1 to 2, then A, if 1 plus 2 equals A is not going to be in the middle. It will lean towards the larger dipole, which is the fluorine dipole. Now if you add 3 to 4, and 3 to 4 will equal B, then if you look at B, B is here. Now this is A, this is B. If you look at how they look like, they are not opposite to each other. A and B are not opposite to each other, so they're not going to cancel each other, and because they don't cancel each other, that makes the molecule to be polar. They will only cancel each other if it was the exact same bonds. The 4 bonds have to be identical. Why polarity is important? We will see in the upcoming chapters. It does determine many properties of the molecule. Polar molecules are attracted to other polar molecules as like opposite magnets, right? So like south is attracted to north, and partial positive will be attracted to partial negative in some interaction that we call intermolecular forces that we will learn about in the next few chapters. Now let's look at these molecules. I want you to pause this video and draw the Lewis structure and the shape to determine the polarity of the molecules. Okay, so water is bent, and we have done water before. The dipoles, all of them are going to be heading towards oxygen, and that will make this molecule to be polar. If you draw the appropriate shape of carbon disulfide, you will see that it is linear, and there is no way this molecule can be polar. Okay, actually the difference between sulfur and carbon in electronegativity does not even allow for polarity. If we do sulfur dioxide, which is this molecule here with a lone pair on sulfur, you will see that there is these dipoles going this way, and then there is the lone pair going this way. They are not equivalent, right? Because these are not equivalent to the lone pair. Lone pairs are always larger, so therefore this molecule is polar. If you do CH4, I wouldn't even draw it. It's carbon and hydrogen only, non-polar. There are no polar bonds here to start with. If you do chloromethane, then we have done this before. This portion of the molecule is non-polar. This one has a dipole going to chlorine that makes the molecule polar. One last thing I would like to add before I end this lecture is if the central atom, I'm going to write it down, if central atom has lone pairs, then molecule is polar unless lone pairs cancel out. So what does that mean, lone pairs cancel out? It's good that I can show you a picture of this. So do you remember that in a trigonal pi pyramidal, for example, I can have a model like this, and although the central atom has 3 lone pairs, they are separated by 120 in a trigonal planar, and therefore they're going to cancel each other out. So these lone pairs cancel each other out, these dipoles cancel each other out, and the molecule is therefore non-polar. Another example I can show you is what if I have octahedral like this one, and I have 2 lone pairs, right? Although I have 2 big dipoles here, they are equivalent in magnitude and opposite in side. They will cancel out, and these here are in square planar geometry. They will also cancel each other out. So this one will cancel this one, and this one will cancel this one, and therefore the molecule overall is non-polar. This concludes the lecture about polarity. I will see you in the next one.